So let's talk about scientific notation and significant figures. Now, scientific notation is basically a way of writing out numbers, reporting them to powers of 10. And usually you put one number in front of the decimal point. So how that looks is, let's say you have 13,984. If I wanted to report this number in scientific notation, I would put 1.3984 times 10 to the fourth. So basically, it lets you talk about a number of any scale as a number, like a number from 1 to 10 with a decimal. So it also works for very small numbers. So if I have a number like 0.000000286, then I can report that as 2.86 times 10 to the minus 7. Now this is very, very, very useful in the laboratory setting where we have to deal with significant figures. Now, significant figures is functionally a measure of precision. And we talk about precision versus accuracy. So accuracy is getting close to a known value or, close to what we know it should be. Precision, depending on how you're thinking about it, can either be you've gotten separate responses closer together, or generally when we're talking about this in the laboratory, it's the precision of your measurement, the finest division you can have of your scale. So in the first way of defining precision, we have this dartboard analogy, which you might have seen before, where you can have low accuracy and low precision, where I'm just kind of hitting all over the dartboard, low accuracy and high precision, where I'm way off the mark, but all my shots are really close together. You can also have high accuracy and low precision, where I'm close to the mark, but my answers aren't close together. But what you really want is high accuracy and high precision. Now, we use the precision both those definitions of precision in the laboratory because almost all of our experiments are going to be run at least in triplicate, because we want to make sure that we got actual real results and it wasn't just something funky happened that just happened to give us an answer we wanted. So if we're precise in our answers, then we're going to be getting similar results over and over and over again, right? So you'll take an average and you can generate like a standard deviation and things like that. So you want a small standard deviation across your different experiments, and that generally indicates that you're getting reliant, consistent, repeatable results, which is really important. But the other way, and probably the more common way you're going to end up using it, especially if you're doing laboratory stuff, is it's the smallest division of your scale. So, if you have a digital scale that reads to 4 decimals, that's pretty precise. If you have a digital scale that reads to 10 decimals, that is a more precise scale because it can give you functionally more significant figures. So a graduated cylinder, which is what's in the picture, is one of the more common ways we use of measuring things. So if you've seen a beaker, it's basically a cup that has, it might have some markings like, 20, 30, 40, 50 milliliters. But if you really want to measure something out, you want to know, do I have 60 milliliters or 64 or 65 or 66? That could be a huge difference when you end up doing your math. So you want as precise an instrument as possible. So a graduated cylinder is significantly more precise than a beaker. A scale that goes to 10 digits is significantly more precise than a scale that only goes to, say, 2 digits, right? So that's one of the ways we can think about precision, and that's probably the easier way to think about it when we're talking about significant figures. So what makes a significant figure significant? Here are the rules, and for most numbers, it's very easy. So all non-zero numbers, 1 through 9, are significant. End of story. Done. Walk away. If you don't have any zeros, every single number is significant. Okay? And then here's how you differentiate between a significant zero and a non-significant zero. If the zero falls at any point to the right of a non-zero number, it doesn't matter if there are zeros in between you and the non-zero number, as long as you are somewhere to the right of a non-zero number. Or another way of thinking it, a non-zero number is somewhere to your left, then that's going to be significant. Okay? If your zero is only to the left of a non-zero number, in other words, it's just a bunch of zeros before you get to your first non-zero number, then those are called leading zeros and they are not significant. So let's consider the number 1356. The number 1356 is all non-zero numbers, so all those digits are significant, right? So all those numbers, that would be 4 significant figures. The number 0.0001090 has both non-significant zeros, and significant zeros. So the first 4 zeros have no non-zero number to their left. They're not to the right of any non-zero number. So we look at that and we say, okay, those first 4 zeros are non-significant. The other 2 zeros are to the right of a non-zero number. So we would say that the first 4 zeros are not significant, but the last 2 zeros are. So this one would also have 4 significant digits. And here's where scientific notation comes in handy. Okay, so for the first number, it's all significant, right? But you can report it as 1.356 times 10 to the third. Well, that small number you can report as 1.090 times 10 to the minus 4. So you can look at that and instantly know, oh, okay, 4 significant figures. Easy. And that's why scientific notation is very, very useful, especially when you're trying to keep track of significant figures. So that's all well and good, but how do you determine when you're doing a calculation, how do you determine how many significant figures you get in your answer if all your values have different number of significant figures? Okay, well, there's 2 rules, one for addition and subtraction, one for multiplication and division. So for addition and subtraction, you want to go with the number that has the fewest number of decimals. So if I take 28.26 and add 10.1, then I get 38.36. Well, if I look at that first number that has 2 decimal places, and that second number has 1 decimal place. So that's going to limit my answer to 1 decimal place because that's the fewest number I have. Okay? So what I'm going to do is I'm going to round my answer. And the way you round your answers, you take the digit that's immediately to the right of your last significant digit. So in this case, the 0.3, that 3 is my last significant digit. So I look at the next number over. If it's a 5 or higher, I round up. If it's a 4 or lower, I round down. So in this case, since it's a 6, which is 5 or higher, I'm going to round up and report my answer as 38.4. Or 3.84 times 10 to the 1. Now, usually with numbers that small, you tend not to report them in scientific notation, but you absolutely can. It's just a little unusual because it's times 10 to the 1, which seems a little weird. For multiplication and division, you take your answer is allowed to have as many significant figures as your starting value that has the fewest significant figures. So we take this calculation, for instance, 23.45 times 1.13 is equal to 621.3898. Okay, that's like the exact value. But if we look at our initial values, 23.45 has 4 significant figures. 1.13 has 3 significant figures. So my final answer can only have 3 significant figures. So I look, first 3, 6, 2, 1, that's 3 significant figures. So I take one, I look one more right, 3, that's lower than 4, so I round down. So my final answer is going to be 621. Or I would report that as 6.21 times 10 to the 2. So let's work a couple examples. All right, so we say, how many decimals are in the answer to the following equation? So we're not doing the math. We don't have to calculate it. We just want to know how many decimals are we going to get. And I don't say sig figs. I don't say significant figures because it's addition and subtraction. The actual number of significant figures doesn't matter, just the decimal places. Okay? So let's look. So the first thing we have is 24.359. Excuse me. 24.359. And we're adding 28.167, subtracting 20.5, and then subtracting 3.005689. Well, the first number has 3 decimals. The second one has 3 decimals. The third one has 1 decimal, and the fourth one has 6 decimals. So, since I'm limited to the smallest number of decimals, my final answer is going to have 1 decimal. How many sig figs are in the answer to the following equation? Now, it's multiplication division, so I evaluate the number of significant figures in my starting equation, and whichever value has the fewest is what determines how many I'm allowed for the answer. So, 60,534, that has 5 significant figures. 0.000012 has 2 significant figures. 24.3 has 3 significant figures. and 0.0101, hold on, 0.01010 has 4 significant figures. So the value that has the fewest significant figures is that second one, 0.0000 whatever 12, has 2 significant figures. So my final answer can only have 2 significant figures. Okay? So now let's actually solve an equation. So 46.5 times 92.1 times 0.030504. And I want to know what's the answer and report it to the appropriate number of significant figures. So when you punch that into your calculator is going to spit out, depending on how many decimals your calculator displays, something like 130.5102964. Okay? But we look at our initial values, 3 sig figs, 4 sig figs, 5 sig figs, and we say, okay, my final answer can only have 3 sig figs. So I need to round. Now I go 3 sig figs, 1, 3, 0. The fourth digit is 5. Say it's a 5 or higher, so I'm going to round up. So I report that as 131 or 1.31 times 10 to the 2. So now I'm going to show you some practice problems. I want you to attempt them first, and then I'm going to solve them out for you. And it's really important that when you do practice problems, it's really going to be most useful if you actually, take the time and pause it. So, find the number of significant figures in the answers to the following equations. 46.53 times 72.035 times 0.000658 times 1684.235. Now, you don't have to solve this problem. Just tell me how many significant figures are in the final answer. All right, so let's take a look. So here I've got 4, let's see if I can draw, 4 sig figs. Here I've got 5. Here I've got 3. And here I've got 7. So my final answer is going to be determined exclusively by which one has the smallest number, which is 3. Okay, next question. I have 1.605 times 10 to the 4th divided by 52.038 times 10 to the minus 46. How many significant figures, again, you don't have to calculate the answer, how many significant figures are in the final answer? Pause the video and figure it out. All right, so here I have 1, 2, 3, or 4 sig figs. Here I have 1, 2, 3, 4, 5. So my final answer can have 4 sig figs because that's the smallest number, right? It doesn't matter that this number is on a scale that's teeny, 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 tiny. What matters is the significant figures.